right, so yes, it really is my great privilege to be here and to have the opportunity to speak to you all today. I know that many of you have actually met me before in my previous incarnation in New Zealand and not realised that I've moved back to Australia. So just to be clear, I am now based here in Perth, although I'm not here very often, so I have epic jet lag. I've just come in from Chicago. Yeah, so the North Americans in the audience are nodding. But I work here now as Director of the Widefield Array, and today I'm going to talk to you about new approaches to wide-field imaging algorithms on next-generation radio telescopes. So this is a bit of a change of pace from some of the other talks that you've had today. Now, because it's late in the afternoon and because a lot of you probably don't really want to see the details of our algorithmics, I've kept this to a very high level, but hopefully you'll take something out of it anyway. So I just want to start by saying this image in the background that you can see here is an image in 3 radio colours of part of the centre of our galaxy, the Milky Way. And so this was actually made with the Murchison Widefield Array radio telescope. It was processed by my former postdoc, Luke Heinsohn, in New Zealand. But this is the sort of thing that we're trying to do to do science. So all of those lovely blue patches you can see are regions of hydrogen gas, and all of those circular yellow features are supernova remnants, so the remains of dying stars. And those are the things that get me out of bed in the morning trying to understand how many of those there are and how they evolved and changed with time. So in order to be able to do that, though, we have to build telescopes which produce prodigious data rates which we need to process on high-performance compute clusters. And if it were not for access to such facilities, we wouldn't be able to do this stuff, and that's really why I'm here. So I'm going to give you a bit of a history of radio astronomy and then tell you where we're at and how that relates to HPC. So radio astronomy actually commenced about 80 years ago with the detection of the cosmic microwave background radiation and a guy called Grote-Reber building the first steerable parabolic radio dish in his mum's backyard, as you do. And yeah, so 80 years seems like a long time, but if you compare it to the rest of astronomy where we've had Galileo and the optical telescope for 400 years, it's actually relatively new. We had significantly a peak of infrastructure investment which happened on a national level, so various countries got excited about radio astronomy in the 70s and 80s, and this resulted in a number of major interferometers being constructed. So the Dutch got out there first and they built this telescope called Westerbork. So this is the Westerbork Synthesis Radio Telescope, which came online in 1970. The US close behind in 1980 with the Very Large Array. If you've seen the movie Contact, that's the telescope in Contact. It's out in New Mexico. And then Australia built the Compact Array, which was opened in 1988. So that's in New South Wales, and that's the instrument I used for my PhD. Interestingly, the same group of people was largely responsible for all 3 of those major interferometers. They were very young when they built Westerbork and got slowly older, but they drove radio astronomy. They're still around, these guys. They drove radio astronomy in those early days in the 70s and 80s when they had a lot of money to invest. Now, this also coincided with a major development in imaging algorithms. So you've built these new facilities, you need to be able to image. And so those 2 pieces of work were done in tandem. After that, we went very happily for about 35 years using those facilities, using those same imaging algorithms, until about a decade ago, we went into what I've called the radio renaissance, which is where we had a new phase of investment in infrastructure. And so that was either in the form of upgrading these existing interferometric arrays that we have, or constructing new ones. So the Dutch built LOFAR, the low frequency array, which is currently the world's largest radio interferometric array. I used to work on that. So that was in 2012, it was opened. The Americans upgraded the VLA, so it's now called the Jansky VLA, in 2013. In Australia, here we upgraded the Compact Array in 2010, and of course Australia also built ASCAP, which I didn't put a picture in, but the Murchison Widefield Array, which is a telescope I'm the director of now, in 2012. Now, interestingly, this peak in infrastructure investment this time did not coincide with major developments in imaging algorithms. So we are still largely using the imaging algorithms that were developed back in the 70s and 80s. And I want to talk to you about why that has driven us to be a particular, in a particular position in radio astronomy at the moment, and what's coming and how we need to change. So these upgraded instruments have increased bandwidths. So you take the VLA, and from Instead of having 50 megahertz of spectrum observed simultaneously, you go up to 2 gigahertz. So this is an increase in data. Or they've got, for the newly constructed ones, very large fields of view. So the low frequency telescopes have extraordinary fields of view. So the MWA telescope that I'm in charge of has a 30 degree by 30 degree field of view. The telescope I use for my PhD has half a degree by half a degree field of view. So this is an enormous difference in how fast you can survey the sky, how quickly you can get to science, if you can process your data. So both these things lead to a vast increase in the amount of data that we have for radio astronomy, and this drives us into a big data era. Now, to graphically illustrate that for you, that beautiful picture that you see there is the radio galaxy Centaurus A. Probably means not very much to you, but it's our nearest neighbour, and that image takes up about 18 degrees on the sky, the height of the image. And the field of view of the telescope that we used for that, the compact array, is about that. So in order to create this image, we have to take lots and lots of images with the telescope, the compact array in New South Wales, and then stitch them together using a process called mosaicing, which is an algorithmic process. In fact, we needed over 400 observations to be able to make that image that you see there. So that took 2 years to collect those data. It then took a further 2 years to reduce those data and make that image. Now that is a spectacular image. That's the most detailed image of this nearby radio galaxy that we've ever made. Fantastic. Right, so that was done in 2011, so that's roughly a decade ago. This is what we have now with the Murchison Widefield Array. That's 2 minutes of data. That's the size of that image there. That's a single pointing. So that shows you how much more of the sky we're actually seeing with these very wide fields of view. So this is upping the data rate enormously. It's less resolution, but it's still cool. All right, so you'd think that would be enough, but we astronomers, we're rather greedy. And so we didn't really want to stop there. So we plan to actually build an instrument which will revolutionise astronomy. It's called the Square Kilometre Array, and what it's going to do is produce the highest resolution, fastest frame rate movie of the evolving radio universe ever. That's my soundbite. That's the sort of elevator pitch of why are we doing this for science. So I'm going to tell you about this project and where we're at to it, and then I'm going to come back to the wide field imaging problem. So the Square Kilometre Array is a currently $1 billion infrastructure project to build 2 radio telescopes. One will be located in South Africa and the other will be located here in Western Australia. And with these instruments we'll be able to do a vast array of science, which I sadly do not have time to get into, but if you want to know what it is, come and talk to me in a break. But it's going to be the world's most data-intensive project. So the 2 instruments that we're going to build, if I can point with this thing, I'll start with the one in South Africa. So it's going to be located here in the Karoo in South Africa. It's going to operate between 350 megahertz and 14 gigahertz, have approximately 200 dishes. The raw data, which comes out of these dishes, is about 2 terabytes per second. That's actually pretty okay, we can deal with that. The telescope that we're going to build here in Australia, which is called SKA Low, and it's going to be located here for those of you geographically challenged where they're in Perth. So this is about 700 kilometres north of us, slightly north east. It's going to operate between 50 megahertz and 350 megahertz and have 133,000 antennas spread out over 60 kilometres. But the important point here is the raw data is 157 terabytes of data per second. Yeah, people have their mouths open. Yes, indeed. That's a lot of data. And we have to, so it's 35,000 DVDs a second, and we have to be able to collate that and process that. So that's going to be close to 5 zettabytes of data per year. So these are big data projects, very, very big data projects. So just to sort of show you in a bit more detail, here's the site in South Africa. This is an artist's conception of what it looks like. Each of those antennas sends 10 gigabits per second to the correlator. The correlator is a supercomputer which is co-located with the telescope. So we'll have one in Australia and one in South Africa, which cross-correlates the signals from the antennas. We use that to make images and other things. This is a radio quiet zone. It's been protected by the South African government through a thing called the Astronomy Advantage Act. So one of the great problems that radio astronomers have is that human beings produce junk which goes across the electromagnetic spectrum. So I'm sure you've all heard of light pollution for optical telescopes. and you want to keep your optical telescopes away from people. The same is absolutely true for radio telescopes. So each and every one of us in this room and this particular audience, I'm sure has got at least 4 devices which are producing radio interference. I know I do. I have 5. So you have to stay away from people. So in South Africa, they've legislated to keep this as a radio quiet zone. So the site here in Australia, and this is the sort of type of antenna that we're going to have. These are called log periodic dipoles. They're up here in the Murchison. It has very low population density. It's 3 nano people per square kilometre, which is an excellent statistic. And it's also protected by a radio quiet zone. So this is in fact the best place on Earth for low frequency radio astronomy. So we're going to have, as I said, 133,000 dipoles over about 60 kilometres, and it's supposed to start some sort of initial construction by the end of next year and run for a decade before it's fully operational. Now, if you want to do this type of science, you can't go from where we are now in terms of HPC. We would need something which is 100 times bigger, faster than the current fastest machine that we've got. So on the way to these things, we have what's called SKA precursors. And so there are 4 of those. They are called Meerkat, Hera, ASCAP and MWA. And so these are smaller scale demonstrators that we can actually cope with. There are 2 each on each of the SKA sites. So Meerkat and Hera are on the South African site, and ASCAP and MWA are on the Australian site. So these are doing SKA related activity and science mostly right now. So this is what they look like. So Meerkat is a 64 element interferometer with these particular type of antennas. These are called offset Gregorians. And in fact, Meerkat will be fully incorporated into SKA mid. So the telescope that's going to go in South Africa for SKA will be these antennas plus about 130 more. Hera's Meerkat is actually owned by the South African government. So that's the other point that I should make, is the square kilometre array, unlike in the 70s and 80s when infrastructure investment was done on a national level, so you could build your interferometer at cutting edge scale by one country, we can't do that. This is a global project. There are 12 countries involved in this work. Hera is run by a consortium of institutions, and it's designed to detect something called the epoch of reionisation, which is the period in the history of the universe when the first stars and galaxies formed. Believe it or not, we don't know when the first stars and galaxies formed. We know that the universe is 13.7 billion years old. We obviously know stars and galaxies did form. We don't actually know exactly when that happened. And so there's a very unique experiment that you can do, and you can only do it with a low frequency radio telescope to actually detect that. So there's a race on at the moment, because someone will get a Nobel Prize if they do it, to actually be able to detect that. So this is one of the instruments that's trying to do that. ASCAP is a 36 element interferometer built by CSIRO. It's on the Murchison. These are the actual ASCAP antennas. And they're doing a survey. They've just finished a shallow sky survey with this instrument, and they're doing some deeper stuff to come. So this is in final commissioning, so is this. And this is the MWA. This is my telescope. It looks like metallic spiders, but it's awesome. So this is also a low frequency telescope. It operates between 70 and 300 megahertz, and it's also designed to detect the epoch of reionisation. So yes, there's 4,000 antennas of the MWA. So the MWA was the first operational SK precursor, so, and you know, I'm the director, so I'm going to talk mostly about that. But Hera's still in construction, these 2 in final commissioning. MWA has been operational since 2013. So we finished the telescope in November 2012, and it's finished commissioning in mid-2013. So we've operated it there for a while. This is the location in a little bit more detail. Geraldton's the nearest town. It's about 30,000 people in Geraldton. It's on the coast. It's still like a 4-hour drive from there to there. So this is Perth down here, and here we have Pawsey. So data are collected here. They're correlated here with the on-site correlator. They're sent down via the NBN network to Pawsey, and that's where we do the rest of our processing. So if it were not for the Pawsey HPC facility, we wouldn't be getting any data out of the MWA. And the same will be true for the SKA. So I think I've said all of this. Just to point out here, this is actually a radio image taken with the MWA. That's actually what the night sky would look like if you had radio eyes, which is quite different to how it would look as we see it with our optical detectors. All right. And now I'm going to try and show you a video just to give you a feel of how very remote it is. Hopefully this will work. So this is a video which zooms in on the site so you can actually see drone footage and so forth of the telescope. We've got 4,000 antennas. They are distributed in lots of 4x4 dipoles into what we call a tile. There are 256 tiles. We have a dense core of tiles in the middle of the array, and then we have individual tiles spread out over 5 kilometres. So this is the site. It's controlled and run by CSIRO. This video was actually made while they were putting some SKA infrastructure on site. And here we have the actual antennas. So here's the MWA antennas, here's a ground plane. Extraordinarily simple piece of kit. No moving parts. It's robust to all sorts of weather profiles, but does a fantastic job of actually doing science. And all of the science has to be done through beamforming, through electronics, and through processing. So again, this is really a HPC telescope, if you like. If we didn't, it's not got moving parts, it's not doing anything complicated, it's the HPC end that's important. So anyway, that's the core of the telescope. These are some of the long baseline tiles. You can see they've got solar panels, just because we didn't want to run cables on the desert. It's very important to protect this environment. This environment is the traditional home of the Wadri Yamaji people, and we go to a lot of effort to make sure that the environment stays pristine and that the Wadri people are happy with the work being done on site. All right, I'm not going to go through this whole video, I'm just going to stop it there. Okay. Now, I wanted to show this, which is actually the data flow for the telescope. So these are all the components which are actually up on site in this remote part of the world. So you've got your tiles, you've got, these are receiver boxes, these go into various pieces of electronics. This is the correlator, which is the computer that we use to cross-correlate the signals. And then we have an online archive on site, which is just essentially a buffer, so that we can then send data down on this 10 gigabit per second link here to Perth to Pawsey, where it goes through some front-end servers into a long-term archive, which Pawsey provides for us. It says down here that there's 30 petabytes of data on a tape archive. There's actually 32 at the moment, and 1.5 petabytes on a disk case. We generate about 1.1 petabytes of data a month with this instrument, so that's nothing compared to SKA, but it's still a lot for us to be able to deal with at the moment. Oops, go back. No, what have I done? There we go. We serve the data through a data portal, also hosted at Pawsey, out to researchers. We have 270 researchers in the MWA collaboration. They're distributed over 6 countries, so Australia, New Zealand, Canada, the US, Japan and China. And I wanted to make a couple of points picking up on things that have been said here at this conference. So for researchers, the location of the HPC is not very important. Remote access is extremely important. So this is very much a regime where we want a supercomputer that feels like cloud. So this was a point that was made early on yesterday. And the other thing is that this is also an example of an HPC centre which is going to be part of a data network rather than a monolithic facility. And SKA will be the same. There will be a set of regional centres processing data across the world which will be federated and serving data out to SKA member researchers. So this is a thing which I think is an interesting space going forward. All right, anyway. My talk, I was asked to talk about challenges of wide-field imaging. So these fields of view that we have with these new radio telescopes are actually so large that we can no longer approximate them as being flat. So we have to deal with the fact that you're actually imaging a curved surface. So you've got a curved surface, you have to deal with projection effects, you have to deal with distortion. In addition to that, the ionosphere causes our radio waves which are coming in to scintillate, basically to twinkle, like stars twinkle. It's exactly the same process. Normally, with a very old radio telescope and a small field of view, you could assume that that scintillation could be corrected for in the same way across your entire field of view. With these very large fields of view, we can't do that. So we have what's called direction-dependent calibration problems, where we have to have a solution which spans the entire image to correct for the distortion. And this distortion happens very, very quickly, depending on how active the ionosphere is. So you can actually have this thing have distortion of the order of 15 seconds. So that produces enormous correction kernels which have to be applied to these data. In addition, because there's large fields of view, you've obviously got a lot of pixels, and so you need HPC to process this. So that's all fine, except that traditional imaging techniques for radio astronomy break down and don't scale. And as I said, we've had this infrastructure investment, but we haven't had the corresponding investment in new techniques. And so we've been working on that. And I was going to go through the details of this, but I'm not. I refer you to this paper. This is a paper which has all of the equations and so forth about one of the ways that we're trying to deal with improving this. The point that I want to make is that step one is to develop new algorithms, which is what this paper does. Step two, which is often missing, is then making them efficient. So step one can't actually usually be done by radio astronomers, or can be done by radio astronomers. Step two generally can't, unless they've got a background in HPC, and most of them don't. There's about 3 radio astronomers in the world that I know who have a background in interferometry imaging and HPC. This guy here happens to be one of them. And so the next thing you want to do is actually look at the implementation. So this is the second part. We actually wrote a paper. This is one of the few papers on how do you improve your algorithmic implementation on HPC to be able to scale up, deal with these data problems that we want to deal with. Doesn't normally happen. So we've got a human problem. So we need these better algorithms. We need to have better implementation. But radio astronomers are so incredibly wedded to the algorithms they developed in the 70s that they don't say, how can we improve the scalability and performance using available HPC? What they say is, let us tell you how to put the architecture of your HPC to deal with the way our equations were written, or our algorithms were written back in the 70s. This is a disaster. This is absolutely not what you want to do, and it's holding the field back. So we've got all of this investment in hardware, and we can't get past this human problem of people not wanting to change, not wanting to adapt, not wanting to learn. So this is a graphic that I made, sort of trying to illustrate this to explain not just to radio astronomers, but to other people. So if you look at effective software design, software efficiency, which are kind of the same thing, this is what we had in the past, least. So this is time in this direction. So these were our old telescopes. They had image sizes of about 1 gigabyte. They were running on PCs done by astrophysicists. Now we've got telescopes like the MWA, we have to use HPC. We've got tens of gigabyte sized images. We need to be slightly better than we had been in the past, but we really need to get up here where we've got very efficient and scalable algorithms which are deployed properly on architecture-specific solutions, because otherwise we're not going to be able to get to science. So that's why we have a human problem. So I don't want to talk about the details of the algorithms, I want to talk about the fact that we need to work with you guys to be able to solve this. And it's not just a challenge to get the actual images, so that's to make the images. There's a challenge then, what do you do with them? So the SKA is going to produce a petabyte of image data per day per telescope. So that's 300 petabytes of data in each country per year. Now, these images look like this. So this is what an SKA image would look like. This is actually a compact array image. Every little dot there you can see, that's a galaxy, that's an interesting thing. All that other stuff is just noise. So only 1% of the pixels in this image actually correspond to sources. And this is a 50 by, well this is not, but the SKA will be a 50 by 50,000 pixel image. And it's not that we don't just look at one image. We want to look at 65,000 frequency channels. So we're actually going to produce a cube. And this cube is going to have 1.6 times 10 to the 14 voxels, of which a very small percentage is actually signal, and the vast majority of it is noise. So if you take that and you put it into an archive, so this is our ingest process. So for the dish array, it's not too much, it's 2 terabits per second. This one, it's sort of 7 terabits per second. It goes into your correlator on your site, goes down to your supercomputing centre, let's say Pawsey. You do some processes, calibrating, you want to get to some science. That needs a 200 to 300 petaflop system, produces your 1 petabyte of data a day. If you store all of that, it costs 100 million euros a year at current prices. We can't afford that. This is science. So, I'm serious. I'm deadly serious. So we've got a problem. We've got 2 problems, in fact. You've got a huge search volume and then you've got a storage problem. So you need to also work with people such as yourselves who are good at AI to get to knowledge faster. We need to extract the knowledge out of this stuff and then get rid of it. Why are we storing cubes of empty voxels? This is nuts. Again, it's a human problem because radio astronomers will say, but what if we missed something? What if the algorithm's no good? Well, the universe moves fairly slowly for most things. Just re-observe. I'm really not being facetious. This is actually, again, a human problem. So when I was a graduate student, the most expensive thing you could do was observe on the telescope. Running the telescope was expensive. Running an archive was cheap. So you had to get your observations right. So this has bred an attitude that you have to keep everything. But now, this is the reverse. Running the telescope, dirt cheap. So re-observing, no problem. Putting all this stuff in the archive and keeping it forever, extraordinarily expensive. But getting people to switch and to flip that is really hard. So another human problem. Anyway, I'm old. So when people think of big data, they think you've got this. So the SK is a bleeding edge big data project. So they think that you've got some nicely structured and coherent, higher dimensional, potentially, set of data from which you can easily apply some sort of algorithm and extract knowledge. My terror is that we've actually got this, which is an unstructured mess. This was an art installation in Barcelona actually a few years ago called Big Data. And I thought this was actually really quite perceptive of the artist. And so what we need to do again is make sure that we've got, the thing on the left and not the thing on the right so that we can then apply the algorithms. So again, we need your help. So when the SKA switches on, even if we have staged delivery, we're going to have more data than we know what to do with. There will be more data than astronomers can deal with. We will be very much like this dog, trying to take a drink and just drowning in the hose of data. And we don't want to do that. So we need to use the experience that we've got from our precursor telescopes. We need new algorithms to be able to dramatically improve this situation and get from collecting the data to science as fast as possible, because that's actually what we're trying to do. But we can't do this without working with communities such as yours. So that's essentially, I think I'm done, my summary. And I wanted to just sort of say, so radio astronomy is this bleeding edge data project. It's a research field which has, I think, rich potential to collaborate with. We've had a serious investment in infrastructure, which is going to continue over the next decade with the telescopes that we've currently got and forthcoming projects like the SKA. It's now time to have a serious review of the algorithm development, but that has to be done in conjunction with the HPC community. So for HPC, people working on AI who are interested in helping with this stuff, I think this has the potential to be a fantastic use case to uncover exciting new things about the universe, which get people like me out of bed, but also potentially to provide pathways to discoveries in related fields. So some of the work that we've done around detection algorithms for radio astronomy can be applied to medical imaging to find tumours. They can be applied to all sorts of other fields where you have to have automated source and feature detection beyond just threshold algorithms, which are very simple. At the moment, the way that we're doing it in radio astronomy is we're eyeballing, we're paying people to look at images and write stuff down, which is exactly how they used to do it 100 years ago with women computers in Harvard. So I bet you didn't know that. The first computers in astronomy were women who used to sit down and just look at eyeball things and write things down. I did that when I was an undergraduate, and I can't believe I paid people 3 years ago to do exactly that still. We're not in an age where we should be doing that. So I can do it now because I can pay 4 people to do stuff for a year on a sky survey on the MWA, but when we get the SKA, I'll have 360,000 times more pixels to look at, and no one's going to give me that number of people to look at this. So we need to do this automatically. But I think there's great opportunity there to have this bleed over into other fields. So we want to go from this unstructured, enormous volume of data to structured data to lead to knowledge. So we need your help. So this is a call to action and to say, if you're interested in this, I'd be very happy to talk to anyone about any of these types of things and in more detail. So the last thing I just want to do is I just want to say as MWA Director that we gratefully acknowledge our partner institutions. So the MWA is led by Curtin University, but on behalf of 21 organisations spanning those 6 countries that I mentioned, and that we wouldn't be able to do what we do without our supporting organisations on the bottom there, including Pawsey. So I thank them sincerely, and if you've got any questions, that's my email address to follow up. Thank you very much.